So welcome to our session. The third speaker that is going to join us, so she won't be speaking, but to have a substitute, Tanika Missouri, talking the emergence of Christian psychology. Our first speaker is Bob Kaita, is a fellow and past member of the Executive Council of ASA, and is an emeritus position of senior physicist at the Princeton Plasma Physics Laboratory, where he conducted nuclear fusion energy research for nearly 4 decades. Most recently, he's worked on finding novel materials for use in fusion reactors. And in the graduate program in plasma physics of the Department of Astrophysical Sciences at Princeton, New Jersey, University, Bob has been the thesis advisor for students who pursued careers in academia, government, and industry. So, welcome, Bob.
So thank you very much, and it's my pleasure to talk to you about nuclear fusion, a Christian's perspective. And I'm very careful about phrasing it this way because it's really my perspective as a Christian, not necessarily a uniquely Christian perspective. And so with that, I'm going to talk very briefly about the basic principles of nuclear fusion, and critically for this talk, the requirements for a fusion reactor. And then I'm going to talk very briefly about magnetic confinement fusion, one of the two mainline approaches, if you will, for fusion, progress toward reactor conditions, and inertial confinement fusion. And one thing that motivated me to give this talk was the significance of recent ignition results, and I'll define what that means. That's been in the press for the better part of the last year. Then I'm going to talk about the advantages of nuclear fusion, really briefly about that, but then ask the question, posed that way, is it then the embodiment of creation care? But then I'm going to go ahead and talk about the practical challenges to fusion energy as an energy source. And is it then, alternatively, a worship of creation at the expense of reality? Then I'll conclude about some comments about lessons from Scripture that might inform on this and some conclusions. So to begin with, I'm going to talk about some of the basic principles of nuclear fusion. What is nuclear fusion? And so for various technical reasons, what we're doing is that the dominant approach of this is to go ahead and use 2 isotopes of hydrogen, deuterium and tritium. Deuterium is plentiful in seawater, and tritium can be bred in lithium, for example. And the products are helium-4, and I'm going to use helium-4 and alpha particles interchangeably. That comes out at 3.5 MeV, and the neutrons, which are electrically neutral, that come out at 14.1 MeV. And in the most broadest terms, this is the most famous equation in the world to look at the mass difference between the original products, or the original fuel, and the final products, and you get a lot of energy out of it. And that accounts for the energy you see there, and the neutrons eventually are used to heat a blanket, boil water, and generate electricity. So what happens is that then people always ask this, what kind of temperatures are we talking about? And we're talking about something in the order of tens of kilovolts to start the fusion reaction going. That's about 100 million degrees. And I'm from New Jersey, as my colleague is, so I have to put up, and here I editorialize a bit. Maybe such temperatures are going to be, unfortunately, more often something that we experience than less. And I'm not looking forward to going back to New Jersey for those temperatures. So now the criteria for fusion reactions was, and this is breathtaking, developed 70 years ago, or almost 70 years ago, in a report that was originally classified, because this is part of the bomb program, by J.D. Lawson of the UK, United Kingdom Atomic Energy Research Establishment, that established certain criteria. And in a way, if you think about that, and I won't go into the details of the derivation, but you say we need enough density, a sufficient amount of the deuterium and tritium fuel. You got to get it hot enough for the DT to fuse. And here's the kicker. Confine the 3.5 MeV alpha particles, which are charged, which in the case of a magnetic bottle that I'll talk about, will hang around long enough to make that as a source of energy, if you will, to keep the fusion going. And we call that burning. And that's the big challenge. And so you take these together, and just because people in our field like to talk about this, they talk about the triple product of density, temperature, and time to be able to go ahead and say that if you achieve those, you get fusion energy. Now, we have two kinds of magnetic fusion, as I had mentioned earlier. Magnetic confinement fusion, or MCF. You heat the deuterium and tritium as a plasma in a magnetic bottle, and I'll explain what that is. And inertial confinement fusion, where you heat deuterium and tritium basically in a frozen pellet in a solid target, and you hope you heat it fast enough so it doesn't blow away, but then go ahead and then fuse and generate energy. So here's then the bottom line as far as progress toward the Lawson triple product, which is density. Yeah, we got the density in MCF and ICF. We got the temperature in both MCF and ICF, tens of keV or 100 million degrees. And here's what's newsworthy. Only in ICF so far have then the alpha particles been confined long enough, and this is newsworthy, so that they could go ahead and sustain fusion. But I'll later on put this into the context of then what this really means for fusion energy production. So for magnetic confinement, but a little technical about it, but what happens is that the way you do it is in a solenoid field. If you've ever played with electromagnets in your youth, you wrap the wire around a coil, or a coil around a nail connected to a battery, you pick up things. You take out the nail and you have a solenoid. And if you then put a container that you can evacuate and you can pump gas into it, the deuterium tritium gas, and then you ionize it, it's going to go ahead and be able to be confined by the magnetic field inside the solenoid. And this is where I've made this joke so often that then students at our program attributed this to me. Fusion is solved if we can make an infinitely long solenoid. And I sometimes get a laugh, sometimes I don't. But with this, what I say then that for the purposes of today's discussion, there are a lot of technical issues having to do with this, but the dumbest, I shouldn't say the dumbest thing, but the most straightforward thing you can do is to bend it around into a donut because it doesn't have any ends anymore. And there are technical challenges with that, but for purposes of today, say that a donut works because you don't have any ends anymore. So after that, you got the gas in there, you got to heat it up to overcome the repulsion of the ions in the plasma. And this is a picture about that. There's an electrical energy hill, where then you get to the point where the binding energy takes over, and you get the E equals mc squared, and everything is wonderful. And then how do you do it? Well, there are a couple of ways of doing it. In the earlier session, we'll talk about high energy physics and particle accelerators. There's at some essential level the same technology of using high energy particle beams to go ahead and heat it up. And I'm not kidding, radio frequency waves that happen to be in the same frequency as your microwave oven in the megahertz range. So, this is, in quotes, established technology that you use to drive the fusion. So then, of course, nothing is ever simple. To actually build a machine, you have to use lots of components of various levels of complexity. You have a pump duct to go ahead and evacuate the vacuum vessel. You have the heating beam that's used to then heat it up. And then you go ahead and you put it in, you use the plasma that you generate inside the vacuum vessel. And my wife insists whenever I give this kind of talk that the person standing there is a normal-sized person and not someone who's vertically challenged like me. So this is to demonstrate that this is a very big machine. So then after that, won't go into the details, but you put in beams of a certain power, you get a certain amount of fusion power out of it from the fusion reactions that occur. And then this is why it's a little bit of a cheat, but we talk about the fusion output power divided by the input power, we call it Q, is close to 1. All right. So then we're close to scientific break-even. And this is work from a couple of a couple of centuries ago. It feels that way. It's in the last millennium, all right, in the 1990s. And so right now, the famous N tau T, the product of the density times the temperature, the confinement time, is plotted on this log scale. And I guess to be fair then, because it's plotted on a log scale, getting close to 1 is almost as good as 1, considering how far the machines have gone in terms of the progress. And there we are in the corner. And if you look at the scale on the right, it says 1970s, 80s, 90s. So it's been a while since we achieved this. Now, what's the problem? The problem is you have to go ahead and confine the alpha particles. You can go ahead and make the deuterium and the tritium energetic enough to fuse, but then there's 3.5 MeV alpha particles. They're a lot more energetic than the energies that you require for the fusion to occur. And so in simple terms, the machine has to be really big. And so to get some reasonable amount of Q gain. And so that's where there's the standard normal-sized person in the Tokamak Fusion Test Reactor that I just showed. And that same normal-sized person is absolutely dwarfed by the machine that's being built right now, and it's still being built. It's being taken decades to build this immensely complicated machine. Okay, so now going on to inertial confinement fusion. Here are the principles of inertial confinement fusion. You have laser producing X-rays that, and there are technical reasons why you need X-rays, but what they do is they rapidly heat the surface, and then the fuel is compressed by the blow-off of the hot surface material. And the core, here then, the physics is the same. The core reaches 20 times the density. In this case, you want to get a really high density and ignites at 100 million degrees C. And the thermonuclear burn then spreads through it and burns out all the DT fuel. Okay, so that's the principle. Now, again, these things are big and complicated machines. So I'll say this again. This is a standard-sized person standing in front of something called a preamplifier module. That's at the beginning of this huge facility, the National Ignition Facility at Lawrence Livermore National Laboratory. And so this big machine aims all this laser power into something that then is about the size of a human eye, all right? And that's where then the fusion is occurring. So then, here I get a little bit technical. The reason why you got to compress this is that, well, in simple terms, there's a solid, it turns into a liquid, and before it kind of blows off due to something called the Rayleigh-Taylor instability, and my children are notorious for recognizing that I do experiments only when my wife is away, when they were little, like going ahead and taking salad oil and water, and then putting the heavier liquid over the less dense liquid, and saying, hey, look at these kinds of phenomenon called the Rayleigh-Taylor instability. And again, my wife would think I'm crazy for doing this and teaching them bad things, but or bad table manners, I should say. But anyway, this is the same kind of thing that you got to really heat it uniformly and fast enough. So then you go ahead and are able to heat this. And that's why we have this thing called a Hallraum, where if you try to hit it directly, it's real hard, even though it might be more efficient, to go ahead and heat the thing before it starts then doing its instability thing. So you do it indirectly. And they call it indirect drive. I mean, surprise, surprise for creativity and nomenclature. So then the significance of the scientific significance of the NIF results is that the ignition occurs, just to repeat, when heating power from the alpha is produced, the good stuff that comes out of the fusion overcomes the loss mechanism and allows the further burning of all the DT fuel until it's gone. And the recent NIF experiments, as I said, are significant because that confinement was long enough for their energy to become the dominant source of the DT fueling. And as a technical comment, they made that little Hallraum, that container, that allowed the implosion of larger capsules to then be the result. So then, the advantages of fusion, what happens is that no carbon emissions, low environmental impact, no radioactive waste or much lower radioactive waste, tremendous energy efficiency, no possibility of meltdown. We don't have a stored bulk quantity of fission fuel, and no concern about nuclear proliferation, unless, as one of the former directors of our laboratory say, the only weapons purpose of the Tokamak, for example, is if you're silly enough to get all the enemy soldiers underneath the Tokamak and you drop it on them. And finally, reliable, firm power, available at all times. And then this is where many people, Christian and non-Christian, say, this is great, and they sit down, because this is perfect for creation care, if it works. But here's the problem. They're the challenges to fusion. Now, this is not meant to be an eye chart, but you have to take my word for it that then, for those of you who are familiar with the space program, there was something that NASA developed called the technology readiness levels, TRLs, that classifies the maturity of the technology from basic research to fully operational. And TRLs of 7 or more are required for deployment operations of something that's practical and works. So what happens is that it all goes all the way down to 1. If you could go over the slides later if you're interested in the details, but suffice to then say you have to have a TRL greater than 1 required for implementation to build the thing. All right. The problem is, and again, this is not meant to be an eye chart exercise, but you have to take my word for it. Is there something called demo? That's something that the Europeans are right now in the midst of planning. And for materials, and later on I could explain to you, after the meeting, if you're interested in what I mean by materials. But suffice to say that the purpose is for this discussion, the TRLs for materials. In other words, the vacuum vessels, everything else that you need to make something of a reactor size is less than 4. And I wouldn't go near a spacecraft, let alone board one to go to Mars or anywhere with this kind of TRL level for a major component. And that's where we are with magnetic fusion. And we have the same thing for inertial confinement fusion. This is the laser energy to that little hull ROM. I'm not talking about the efficiency from going all the way from the preamplifiers to that hull ROM, that thing that looks about the eye size. But this is the efficiency we have right now. It's like 20% of the laser energy. So of that 20%, if you then do the math, for that 20%, you're getting more energy out. And here's the kicker. We have to reduce the time between shots. That's basically 1 experiment a day to like 1 shot a second, maybe a few seconds, for this kind of thermal cycling. So then fusion looks like chasing after the wind, to use all right. So now what are the lessons from Scripture? Now, does Scripture support either position? Forget it, or it's a panacea. And I was thinking about that looking at Isaiah, 44:17. I'm not going to read all the verses, but I think they're very familiar to you, and you could look it up on your leisure. Well, the thing to point out is that the carpenter goes ahead and collects the wood. He uses it, it's the fuel for burning, to heat himself, bake bread, but then he also fashions the god and worships it and makes an idol to bow down to it. But then, the thing is, if you look further detail, there are verses and verses and verses describing the benefits of God's blessings in terms of then what you can do with wood. Half the wood he burns at the fire, over he prepares his meal. He roasts his meat and eats his fill, and then warms himself. Ah, I am warm, I see the fire. From the rest he makes a god his idol and bows down to it. And I ask, why does Isaiah describe all of this? So then, in that right mindset, you can say deuterium and tritium can be used for fuel. Praise God for that. And so be thankful for the laboratory, the ability to demonstrate controlled fusion. We've gotten it in almost in magnetic confinement, and maybe this could justify further development in the future of the materials. And that's what I spent the last couple of decades of my career doing. And then similarly, I see the fire. Be thankful for the ability to achieve burning plasma in the National Ignition Experiment. Now, here's the thing. This is not going to be a debate on whether or not Christians should be involved in nuclear weapons or the morality of nuclear weapons. And that's been a debate since Oppenheimer. And I'm not talking about the release of the movie. Okay? It is important this is what the American taxpayers are paying for. It's important for benchmarking models used to evaluate stockpiled nuclear weapons, and the need to constitute and improve the capabilities of underground testing, because we can't do that anymore. So then this is critical information to benchmark the models so we don't have to do underground testing anymore, but still look bad characters in the eye and saying, you better not even threaten to use nuclear weapons because we have the scientific justification to make sure that our weapons work. All right. So then, what are the conclusions? The conclusions are, believing that promise of clean infinite energy is the only justification for fusion underrates the challenges that remain. At the same time, believing that fusion will never work can blind us to its intrinsic worth of our accomplishments. Both views can be fraught with difficulties. So what I conclude by saying is that our identities tell us how we view our work. If we are Christians first and foremost, we thank God for our achievements because we see the blessings, that whole beginning of Isaiah, what they are in themselves, 14 through 16. But I think people are too quick to jump to the last verse of the section. If we are scientists first and foremost, we thank ourselves for our achievements because they can save us, because they are our gods. Thank you.
Thank you for your talk. I'm Charles Hunt from the Electrical and Computer Engineering at UC Davis, and all of my research and all of my graduate students work at NIF on TASE. And I agree with you that as believers, it's very important that we not chase after wind. But I think that you have neglected a very important point about NIF, and that is that it's an experimental facility to demonstrate the capabilities of the individual steps, whether we're talking about the target, whether we're talking about the lasers,
Absolutely.
the optics, the triggering, the X-ray diagnostics, and so forth. Nobody ever intended this as a energy production facility. The goal, if we're just talking about energy production, is specific to try to generate an energy production facility. And actually, on every one of the points that you said, we should look into these as materials, those are not below 4 on the technology readiness level. They wouldn't even, as of December last year, have said, we want to move forward with this with the level of aggression. I mean, all the students I can recruit want to work at that place. And they are really excited about, in the next 2 to 10 years, the fact that this will be brought to market, as well as ITER. They're different scales, so they'd be used for different things. I think it's really important that we look at it for what it is, not looking at it.
Exactly. Yeah, no, and that's the thing. And so
the technology to do, by the way, it's not 1 shot a day, it's at least 3 shots a day, 365 days a year. But that's an experimental rate. And the target from 12 years ago has always been to do 6 shots a minute. And the technology has been outlined on how to engineer that for just exactly that in an energy production facility where nothing has ever changed. Whereas at NIF, everything has changed almost every shot, specifically for the experimentation. So we're really talking about apples and oranges here.
Yeah, and so, but this is precisely the point. I mean, I'm very intimately involved in what's going on with NIF. In my work, I mean, I even have a student who's the head of the weapons development aspect of NIF. She's a group leader at NIF. And I'm also just, if you want to then go ahead and talk about this, I'm the editor of Review of Scientific Instruments. And we're going to have a whole series that I've edited on all of the technology of NIF that I think is exciting from diagnostics. That's what I spend most of my career doing. So the thing is, I just want to say that I don't underappreciate the purpose of NIF, but this is to call attention to the fact that then you hear for the last year things that didn't even bother the people I know in DOE, who then say, oh, energy is right around the corner, and all these startups that are promising this around the corner. This is what I'm saying. So that I don't want to get into a technical discussion and we could sit down and you want to talk about all of these. I'd be quite fun, I'd be quite willing to do this. And I know exactly what you're talking about. And I don't want to quibble about 1 shot or 3 shots, but to point out that then there is this problem of then going ahead and selling it if, as scientists, we're first and foremost going to try to justify this.
Okay, so maybe you guys can talk about it later. Another question here.
Yeah, thank you for your talk. And so on a follow-up on your comment, it's right around the corner. I didn't see a timeline on your scale to get to the demo, whatever that TR scale was. What kind of projected timeline, even if it's dashed, would we be looking at? Obviously nuclear fission has its difficulties, but it's certainly picking up steam nowadays, even in the green camp. But I'm just curious, your opinion, not to hold you to it, but yeah, what kind of timeline there?
All right. This is then an issue that's very fraught. Because what happens is that, all right, here's the dirty laundry from the European, Fusion Energy Development Agency. This is from a report that you can look up, on the Journal of Nuclear Materials. It's up to the point where there's so much political pressure to start the demo design that in the demo documentation provided by the EFDA, the European Fusion Energy Association, they actually say the materials problem is not solved, but we're going to go ahead and we're going to start designing demo and even building it with the hope that then we can go ahead and get it done. So they want to start demo design in 2030. All right. So, that's, to use a crude analogy, we're going to build a Saturn V or whatever rocket is your favorite for going to Mars. And we hope that then the tanks for containing the fuel, we don't know how to build them, will be ready by the time that we're going to assemble the rocket. At least to me, being involved in it, it's that kind of craziness. So that's why these numbers are crazy from the startups, if we don't mind my editorializing. They talk about 10 years, 20 years. But these are the kinds of hidden assumptions there that people are not to come clean with. And then we as Christians, I'll be blunt, have a responsibility not to be a part of it if we're involved in this kind of thing in this field or any other field.
Yeah, so I think pretty much any way we try and make electricity, there's an environmental downside. So I'm curious, what are the environmental concerns with this method?
That's, I think, a hard question that I don't think I can fully answer just because there's so many technical unknowns in actually making this practical. This is not what's required to generate, already before you have a breeding technology to generate tritium is a technical unknown, to go ahead and get this kind of fuel. And, what are you going to do to generate, tritium? Right now, we have to rely on facilities, nuclear facilities, that will then generate tritium, like Canadian facilities to generate tritium, that kind of thing. So these are kind of linked problems that are related to other industries, like the fission industry, for example. If you then do your bookkeeping to then go ahead and see what's inside a power plant, or not too many, besides relatively low-level waste that are in the components. But then there are enough uncertainties to know then I wouldn't, hazard a guess as to then what are the ultimate broader environmental impacts of it. That's the best I can do right now.
All right, thanks a lot.